Hello, my name is Alex May. I'm a graduate student at UC Santa Barbara, and today I'll be presenting our paper, Foveate, Attribute, and Rationalize toward Physically Safe and Trustworthy AI. This presentation may contain some examples of harmful text, so if you're uncomfortable at any time, please feel free to just look away. The current age of digital media has raised concerns about people's physical safety. Unsafe language can come in many forms. First, they can be overtly unsafe in that they are characterized by explicitly violent keywords. Second, they can be indirectly unsafe in that they are not actionable statements but encourage future events that may lead to physical harm. Our work instead focuses on covertly unsafe text, which is still physically unsafe but requires an additional element of reasoning to be used. For more background into covertly unsafe language, please refer to our previous works. Because covertly unsafe text requires additional reasoning, it is important not only to be capable of identifying such text, but also explain why such text is unsafe. This leads us to our central research question: can language models correctly identify and justify whether various actions are safe or unsafe in different scenarios? To answer this question, we consider three main design goals. We want our solution to be explainable in that we provide human-interpretable insights into the reasoning process, credible to provide information from credible sources, and verifiable, allow users to easily fact-check a generated rationale. The criteria was chosen to align with a user-centered ideology toward transparent AI that provides stakeholders the resources to decide for themselves whether or not to trust an AI system. FARM is our attempt at a solution that meets such design criteria. It is a pipeline approach consisting of three main steps. First, for a given safety scenario, we must first foveate or identify the focus of a scenario. Then we use this foveation to query credible external sources to attribute to. Finally, we pass the retrieved sources and knowledge into a language model to generate a verifiable rationale. I'll now go over each step in more detail. The foveation task is a text completion task guided by few-shot demonstrations to identify the focus of a scenario. Compared to existing work, our foveation task is unconstrained to capture the complex nature of a safety scenario. To select our foveation, we use greedy decoding to approximate the maximum likelihood foveation. By performing explicit foveation, we aim to both denoise and add intermediate interpretability into the reasoning process. To use a concrete example, a user may ask a language model whether they should taste a colorful mushroom they encounter on a hike in the woods. We prompt the language model to explicitly generate this foveation given the scenario, and this is the result. Once we have identified our foveation, we seek to attribute it to external sources. This design choice provides a time-agnostic solution with naturally built-in attribution. We consider three sources that balance generality, credibility, and scalability. An open domain web search, such as Google, is the most general and unrestricted choice. For a trade-off of generality with credibility, we try filtering Google for specific website domains. Finally, we consider Wikipedia as a knowledge base with a layer of fact-checking that maintains a large-scale generalized knowledge. In our concrete example, we extract information that colorful mushrooms may relate to mushroom poisoning, which has numerous physically harmful effects when consumed. With our attributed knowledge, we pass it back into a language model to generate rationales. Once again, we use greedy decoding as a mechanism to mitigate hallucination. Our few-shot demonstrations additionally help us to format our answers in the form of a template. In our example, we can see that our pipeline approach generates a correct rationale that explains why tasting wild mushrooms is unsafe action. To show our classification results, we see in this table that we actually gain an impressive increase in accuracy compared to the baseline reported in the SafeText paper. For a more fine-grained analysis, we compare different variations of FARM with respect to the attribution source and number of sources we use. We hypothesized that Google Credible shows peak performance compared to Google Base and Wikipedia as it balances reputability with data and reputability and reliability with data availability. For the number of snippets, too many potential snippets would result in too much noise for a model to reason effectively. However, too few snippets could rely on too much dependence on the ranking system itself, potentially increasing the amount of irrelevant knowledge or misinformation. We find an optimal balance at 3 snippets. Next, we dive into a fine-grained error analysis of our generated rationales. The first type is a factuality error, where generated rationales contain incorrect information. We compare farm to a baseline without the foveation and attribution to general knowledge, or external knowledge rather. And the baseline, as you can see here, may hallucinate without grounding to this external knowledge. Farm fixes such an issue, but again, may suffer from external information in highly polluted environments. Entailment errors occur when generated rationales do not entail the conclusion. The baseline, as a result, may underdevelop explanations that are supposed to lead from the action to the harm. Farm benefits from sources that explicitly state such logical connections. Finally, attribution errors occur when the source does not match the information stated in the rationale. The baseline may hallucinate non-existent sources in the rationale, while farm's attribution step can naturally retrieve and generate these specific links without any hallucination. For more background, principal mathematical formulation, as well as supplementary experiments and analysis, please refer to our paper for more details. To conclude this presentation, we established FARM as a problem-solving technique that first foveates on missing knowledge, retrieves it, and attributes it to trustworthy sources. Then, it is utilized for in-context inference to generate human-interpretable rationales. FARM is a time-agnostic solution that is easily verifiable. It achieves state-of-the-art performance on SafeText and improves faithfulness, entailment, attribution, all of these abilities while generating rationales. While we discussed FARM exclusively today with respect to physical safety, a promising future direction is to apply FARM more generally in other domains. If you're interested, please check out our code base, linked at this GitHub link, and reach out if you have any questions. Thanks for listening to today's presentation.